So when we first started talking about forces, I asked you, sitting down, how many forces you were being subjected to. Some of you said 1 force of gravity. Some of you said 2. Okay? The answer is actually 2. Because if we did not have this other force that counteracts the force of gravity, what would happen to us? We would sink, we would continue sinking through the planet because that force of attraction is so strong. Okay, now that doesn't happen because there's another equal force, yet opposite in direction, that's acting on us at this very moment. I'm standing on this floor and I'm not sinking through it because not only do I have a force of gravity pulling me towards the center of the earth, but I also have what's called a normal force, which is pushing me, it's the floor which is pushing me back up. They cancel one another out. Okay? Now, the normal force, also known as Fn, is also a vector. It is always going to be perpendicular to your surface. So it's nice and great if the surface is horizontal. I'm going to have my force of gravity going downward, and I'm going to have my normal force going upward. Now, had I drawn these to scale, they would have been equal in magnitude, opposite in direction. Okay? When we get to Newton's laws, we're going to find out that an object at rest wants to stay at rest. An object in motion, in uniform motion, is going to want to stay in motion. And they're going to require, these objects are going to require additional forces to cause them to move. So if I'm standing here, okay, I've got the force of gravity bringing me down. I've got the exact same normal force bringing me up. Why don't I float away? Because these forces cancel out, and it's almost like there's no force acting on me. I'm at rest. I want to stay at rest. Okay? If I have an inclined plane, all right, which is this right here, okay, a ramp, where is the normal force going to point?
It's going to point upwards but perpendicular to the...
It's going to point perpendicular to the surface. Force, and here's where it gets interesting, and this will be chapter 2 after the break, but gravitational force, it doesn't matter what kind of surface you're on. Gravitational force is always, always, always at 270 degrees south, straight down. Normal force, on the other hand, is always going to be, so if I have a box here on my inclined plane, gravitational force is always going to be straight down. Okay, and it's going to, the length of the arrow is going to depend on the mass of the object. Normal force is always perpendicular to the surface. So the only time these cancel one another out is when you have a flat surface. If you don't, their magnitudes are still the same, but their directions are no longer the same. Do you see that? Because the normal force is always perpendicular to whatever surface. If this is on an incline and I've got something resting on it, okay, it's that surface that it's exerting the normal force upwards. So the normal force is coming from this surface. It's not coming from the planet. And the surface happens to be at an angle. So the normal force is always perpendicular to whatever surface you're on. Now, we're not going to necessarily worry about this right now. We will look at inclined planes later, much later. Okay, but it's just to tell you that normal force and gravitational force don't always cancel one another out. They cancel one another out when you're on a horizontal surface. That's about the only time. Okay? The formula for the normal force is exactly the same. It is going to be, all right, Fn is going to be equal to the object's mass times gravitational acceleration. But when instead of actually, when we looked at the previous video where we talked about gravitational force being downward, this one stays as a positive number because the force is pointing upward. Okay, it is always going to point in the positive y direction. Okay, that's why it has a positive direction. It's never going to have a negative to it. If we look at the example on page 9 of your notes, okay, what is the normal force exerted by a table supporting a 13 kilogram box? So if I have a table like this, okay, and I have a 13 kilogram box on it, right now, I'm going to be looking at calculating the normal force going in this direction. So in order to do that, Fn is going to be equal to the mass of the object times gravitational acceleration. Do you notice how these formulas are eerily similar? They are. The gravitational force formula is going to be used time and time again. If we look at the example on page 9, it actually gets you to solve for Fg, and then it changes the direction. So if we want to solve for Fg, this is our formula. We get our 13 kilograms times g, which is 9.8 meters per second, which gives us, per second squared, 127 newtons of force downward, right? But in reality, we know that the normal force is not acting downward, it's acting upward. So this ends up just being positive 127 newtons or 127 newtons upwards. Now, to make matters a lot simpler, to not have to actually go through the whole idea of the gravitational force and then changing the sign, you can easily just write in an n here, and it's the exact same equation. It's always the exact same equation. Okay? So you can actually skip this step here, and you end up being left with a positive number.